I'm going to do a pretty complex example here that is very simple if we use the tools that we've learned with regard to probability and probability multiplication. So we're going to do an analysis of a COVID test and identify its effectiveness on, say, a college campus. So if we know that 2% of the people running around have COVID and are asymptomatic, and we want to test all the asymptomatic people, and we want to figure out which percent or who's likely to have COVID, this analysis is going to be quite enlightening and maybe a little bit counterintuitive, but at minimum, it will help you get your homework done. Okay, this is a fun problem that it may lead to some interesting conclusions or some interesting findings, but let's go through the data. This is like one of the problems on the homework set. And so let's just try and make heads or tails of this and understand how our knowledge of probability and events can really lead to some shocking findings and some important findings, especially in this day and age of COVID. So of all the people, then I made up these numbers, but they may be close. So of all the people walking around and aren't showing COVID symptoms, 2% actually have COVID. So in other words, we're going to call them, asymptomatic carriers. And so we want to know who those people are. So I developed this test that is 99% accurate in identifying someone who is known to have COVID. So if I give this test to a random person to a person who's known to have COVID, 100 people, it will tell you 99 times that they have COVID, and one time it will be incorrect and it will say that they don't have COVID. So that's 99% accurate. And then for someone, the tests always don't work the same way in the positive cases and the negative cases. Rarely they do. So usually they'll have a different number. So for someone who is known to not have COVID, so if I take 100 people who do not have COVID, it's 95% accurate. So in other words, 5% of the time it will say that they do have COVID. So if I take 100 people, then it will tell me 95 that don't have COVID, and I know that for a fact. It'll tell me 95 of them do not have COVID, but it will incorrectly tell me 5 of them do. So again, if someone's known to have COVID, it will 99 times out of 100 tell me the truth, and then one time it won't tell me the truth. But if they don't have it, it'll tell me the truth 95% and 5% otherwise. So the question is what is the probability that a random person who has a positive test for COVID using my test actually has COVID? For those of you who really are interested, this 99% number is also called, this 95% number is called specificity, and this 99% number is called sensitivity. You don't need to know that, but that's just of interest. Okay. So what is the probability that a random person who tests positive for COVID actually has COVID? So let's start to put this in terms that we understand. So let's make some notation. So let's say C equals, the percent that, you have COVID. You have COVID. And then C prime would be not have COVID. So these are some variables that we're just going to use. And then, so the probability, we know there's 2% have COVID, asymptomatic people. So the probability that you have COVID is 2%, 0.02. The probability of C prime then is what? It's 98%. You probably don't have COVID. All right, so now let's do the other thing. Let's do the other variable that we know, which is T. Let's call a T as someone who tests positive. Well, we don't know in the general population right now. This will be test negative. You test negative, not positive. not positive. And so we don't know what the probability, we're going to call that the probability of T and the probability that you'll have a negative test, but we don't really know because it's some mixture of something. We don't know the answer. All right, but let's see, what else do we know? What is this 99% number? It's 99% accurate in identifying someone who is known to have COVID. So given that you have COVID, the chance that you test positive is 99%, right? That's what that's saying. 99% accurate. Given that you have COVID, it's 99% accurate. So the probability that you'll get a positive test is 99%. Likewise, let's look at the 95% number. And that's telling you that the probability, if you are known not to have, given you do not have COVID, and then we know that's true, then the probability that you test negative is what? Think about it. 95%, right? So if you take those 100 people in the cohort of people who do not have it, then the chance is 95% that you'll get a negative test, and meaning a 5% chance that you get a positive test. So you could actually also write this, the chance that you get a positive test given that you're negative is 5%, and the probability that you get a negative test given that you have it is 1%, right? These logically flow, but we're not gonna need these numbers, okay? But what are we trying to answer? So this is what we know. So given that we know all of this, we can actually answer the question using our rules of our multiplication rules of probability. So what is the probability that a random person who tests positive for COVID is using my test actually has COVID? So we're trying to find, so let's put this in a different color. We're trying to find, let's use a totally, really different color. This one, blue. This is what we're trying to find the probability that you have COVID given that you have a positive test. So we're looking for this, right? And we don't have that. We have it the other way around. We have the probability of a positive test given you have COVID, but we want to know now that if we go out and test a random person and they have a positive test, so we take 100 people who have positive tests, we want to know what percentage of them actually have COVID, and we don't know that. So we do know a number of formulas, though. We do know some formulas. So if we're going to try and back into this one, we're going to need to use our formula that says, well, if we know the probability of C intersect T equals the probability of a positive test times the probability of C given a positive test. So that's the formula that relates, that we can use to find this. So to find that, then we have to now find P of T and the P of C intersect T, which we can find because what? We can use this formula here in this formula to start to make sense and get more data. Okay. So let's use our smarts here. So we can again we're going to use this formula and this formula, and we're going to say, well, the P of T intersects C, which is going to be something we need here. Well, let's write it the other way around, just to make it look exact, because C intersects T and T intersects C are the same thing, equals, let's use these things that we know. The P of C times the P of T given C. Okay? So that's 0.02 times 0.99, and that equals going to be 0.0198. And now let's build a chart over here that's really going to help clarify some things and help us out. So there's 4 cases, and they're all mutually exclusive, that we have COVID and we have a positive test. And that's, we have COVID, that's like COVID union, a positive test, or sorry, intersection, positive test. Then there's a chance that we don't have COVID. So we have don't have COVID and we get a positive test. Hopefully that's a lot less. Then we have the possibility of we have COVID and we have a negative test. And then there's a chance that we don't have COVID and we have a negative test. Okay, so, and we know also that the sum, the total of these 2 boxes has to be 0.02 or 2%, because 2% of the people have COVID and 98% do not have COVID. So this sum has to be 0.098 or 98%. Well, we just figured out this box, this top left box, and so we know that that's 0.0198. So if that's 0.198, and then we know that this box has to be 0.02 minus 0.0198, because these 2 boxes have to add to 0.02. So if we do that subtraction, we get 0.0002. And so if you add those 2 numbers, they get 2%. So let's do the same thing to find this box. So what do we know? We know that the P of C prime times the P of T prime given C prime. So again, the probability of everyone who does not have COVID times the probability of a negative test given that you have COVID should equal the probability of C prime intersect T prime. And that'll give us this box down here. Okay, so that's, again, we're looking at this number and this number. So 98% of people do not have COVID. And then in those cases, the test 95% of the time correctly identifies you. So if we multiply those 2 numbers, we get 0.931. So 0.931. I'll put a 0 here so we carry everything out to 4 digits. And so if we subtract this from this, we should get this, because remember, the total C prime is 98%. So 0.9800 minus 0.9310, that gives you 0.049. Now we can do the same thing. Like if these boxes total to this number, we can go out here and we can find the sum for positive tests. So this is the number of positive tests we'll get. And so if you add those 2 boxes together, you get 0.0688. 6.88%. And if you add these 2 boxes together, you don't have to do this for the purposes of the problem. You get 0.9312 or 93.12%. Great. So now we're almost to so this is, again, 6.88%. That's the number of positive tests we're going to get, and 93.12% is going to be negative tests. So now we can answer our question, because remember, we're looking for this piece, and now we know this piece and this piece. So let's write that down and let's solve the problem. Let's do it in a different color. Probability of C intersect T, which we know, that's this, 0.01998 0.0198 equals the probability of t, which we know is now 0.688 times the probability of having COVID given that you have a positive test. And so that's kind of like our x or whatever. So that's going to equal 0.0198 divided by 0.0688. And if we take out our calculator, 0.0198 divided by 0.0688, that equals 28.77, which is 28.8%. Wow. The probability, if we have a positive test, that we actually have COVID is only 28%. It's less than 50%. So it's terrible. So what this is telling you is that, so let's go back to our second question. Is this test good enough to deploy at a college campus? I would say it's probably not, because you go around testing people, and if, roughly 30%, only 30% of the time the person tested actually has COVID, you need to get that test rate up higher. So you need to get this 98% number, 95% number. I'm going to tell you right now, you need to get it up closer to 98 or 99% before you can deploy it on a college campus or in mass. Or you're going to be scaring a lot of people. Or at least that's my opinion. So we'll call that a wrap, and we'll do some more problems on a separate video.